represented as a triple index that's an offset from 0, 0, 0. And I know my bin because I know things like my thread ID and my thread block information. So, again, each thread accumulates atom forces and energies in the registers. The bin neighborhood index offsets are stored in constant memory here. So then we load the atom bin data into shared memory, and the atom data and bin depth, okay, so the maximum number of atoms that could be stored in a bin, are carefully chosen to permit coalesce reads from global memory. I'll tell you a little bit more about the data organization in the subsequent slides. We check for and omit excluded pairs. Then the thread block will perform a sum reduction of the energies. And then there's a coalesced writing of the forces and energies with some padding to make this coalesced back to the GPU global memory. And then later, the CPU copies this output here, the global memory contents, and then we'll finish summing the energies from the bins. So I'm showing you my data structure for just storing the information for a single atom, and then these things are collected in an array to form all of the full contents of a bin. This is a useful union that I use so that I can go ahead and read arrays of these things as flints, and then I can use them as floats or as ints or unsigned ints. So the way I'm choosing my bins here is a bit different from the way NAMD does it. NAMD is choosing a bin that will fit the cutoff distance plus some sort of extra margin there so that you can also take care of the hydrogen atoms that are attached to the heavier atoms, and also some extra margin so that you don't have to just update the bin hashing every single step. And so NAMD's bins are quite large, and so they contain a bunch of atoms. The approach here is to say that, well, there's given the architecture underneath, there will be a nice size for these bins based on those considerations. And so here I'm calculating an ideal bin volume, and then I'm choosing a bin length, and I will go ahead and maybe make this bin length a little bit smaller so that I can equally or evenly tessellate a periodic cell with this.
He has a question.
Oh, well, yeah. I think you were addressing that. Why did you need bin fill to be not more than half?
Well, because if the bins are too full, where do the atoms go? And so I only have fixed size for these bins, right. and so by using a bin fill ratio here when in this equation for the ideal volume, I'm taking care of the case where maybe sometimes there are enough atoms packed together in a certain region or a certain volume of your system that will actually, although the density is still the same over the entire system,
And you know the density a priori?
Oh, well, we're sort of using a rule of thumb here that's 1 atom per 10 angstroms cubed. And
can you comment on how like polarizable force fields impact the particle density?
well, sure. One recent addition to NAMD is the Drude model with Drude oscillators and extra Drude particles and some lone pair charge sites. And so all of that is going to be adding or increasing the density by about a factor of 5/3. And so the density really is related to the underlying model, but this is what works good for just your standard atomic simulations for systems of biomolecules.
So this is hard-coded within MD, right? This is hard-coded in MD, right?
This is code that is not in NAMD. So this is in a framework that we call NAMD Lite that we use to test for this. And actually, this is submitted as a parameter. I'm just showing you values here so that you don't just look at this and have no idea what these things might mean. So I'm giving you some real data there.
Those things could be computed from your periodic cell size and particle transfer.
And you might even not even want to fix the bin depth. I mean, here the bin depth is chosen to be the thread block size, but maybe this changes depending on whose hardware you run. Maybe you use a larger number here for an AMD GPU than you do for an NVIDIA GPU. So then here I'm showing code for the outer loop over the neighborhood of bins. I guess one thing I didn't mention is that these things are being stored relative to the centers. So the positions are being stored relative to the centers of the bins. That's just to maybe increase, gain a few more bits of precision that way. So this is the math that's looking up the neighborhood offset here and calculating the difference between the bin centers that you're going to need to add into the pairwise calculation. You might also need to adjust the bin indices here to take into account periodicity. So you might have to take these IV, JB, and KB values and wrap them back around your 3D grid of bins. And so then this is the code that where the thread block collectively loads the next atom bin into the shared memory. And so then on the next slide, I'm going to show you the loop over the atoms in the bin in two parts. So here's the first part, where we're looping over the maximum depth of the atoms, and if there are no more atoms remaining, we just break out of the loop early. Okay, we have relatively little work if we are outside of the cutoff distance, but if we're inside the cutoff distance, then we have a lot of work that we have to do that's also continued on the next slide. But the advantage then of using smaller bins, like this code does, is that you are more likely to have this test succeed, so that you are, whereas if we have really large bin sizes and we bring in a bunch of atoms, but most of the tests fail, we've kind of wasted the work that it takes to actually copy those things to shared memory, to loop over them, to calculate these pairwise distances. With a smaller bin size, maybe we're increasing this to something like a 25% to 33% success rate here with this cutoff test. And so we go ahead and test exclusions explicitly. And now if there is, and if we find that the interaction needs to be excluded, there's still some stuff to calculate, and this is basically the correction of the long-range part that will automatically get added in that we need to go ahead and subtract off of the electrostatic interaction. And so that's what this code is showing right here. And so now for the second part of this, if the interaction is not excluded, then we have a lot more work that we need to do for both the electrostatics part and for the, maybe just a little bit more for the electrostatics part, but a lot more for the van der Waals part. This takes care of the switching function down here. Then finally we add the contributions into the forces, and we sum the energies. And now here's a slide that just shows you how the energies are sum reduced over the thread block. And so this might be of interest because this is a fairly efficient way of doing it that's taking advantage of the warp size here.
So the GPU hardware has the property that you can have threads within the same warp doing updates to shared memory without the need for sync threads calls. And so if you know that you are at the stage of your reduction that you're down to a single active warp, you can basically remove all those sync threads calls, and you can see, so in Dave's code there, show them where the loop is, show the loop part. The upper,
Oh, I'm sorry.
point at it with, yeah, that.
I mean here, this
So,
loop right here.
and you begin by doing a reduction over the entire thread block, and you basically have the number of active warps in each step, so it takes a logarithmic number of steps to do this reduction. And once you have just one remaining warp, then you no longer have to do those sync threads calls, and that makes the last 5 steps in the reduction very, very, very fast. And so this is something to consider. Anytime when you need to sum a bunch of per thread results from your thread block to get one set of answers, or accumulate some value, whether they're forces or energies or whatever, this is something to consider. Can you organize your data in such a way that you're either doing it entirely within warps like this, so you can use that logarithmic number of steps without the sync threads, or at least minimizing the number of sync threads calls that you have to do. So something to keep in mind.
Yeah, so I actually have some shared memory space set aside for an array of forces and also energies, and so then I'm basically summing these over all of the threads in the thread block, and so I end up with an array of partial sums, except for a couple of special sums that are specially designated that actually have the entire result in them, and then those are what end up getting written out to global numbers.
Just a quick question. If your reduction vector is sufficiently large, in the early stages of your for loop, is it more efficient to kick off different versions of your kernel with different thread or block sizes so that you're fully using the device? Because here in your for loop, you're decreasing each time by half the amount of warps that you're using.
Yeah, so this is one of those interesting things. So your GPU SM actually only runs at most 1 warp's worth of threads at a time physically. If you have nothing else to do than the reduction, then you only have the number of active warps in that thread block within itself to overlap its own memory access latency. But since you're doing this reduction in shared memory and not global memory, you're basically running at the full clock rate. You're not taking those hundreds of clock cycles of latency, so the latency hiding isn't as important as the throughput of those instructions.